It's often useful in mathematics to be able to estimate the value of a function. Rather than calculating the exact value, if we can produce an accurate enough estimation, we can reduce the number of calculations involved. Computer software that uses these functions can then produce reasonably accurate results in a much shorter amount of time. Here we have a binomial expansion for 1 plus x to the power of 6, and we could use this, for example, to estimate the value of 1.01 to the power of 6 if that was needed in a calculation. So I'm going to show you how we can approximate the value of 1.01 to the power of 6 just by doing a few calculations rather than doing the full 7 terms, calculating all 7 terms and adding them together. So if we write 1.01 as 1 plus 0.01, then 1.01 to the power of 6 we can calculate by substituting 0.01 for x in our binomial expansion. Okay, so if we go ahead and do that, just replacing x with 0.01, you'll see as we progress down the expansion, we don't actually need to do all of the terms. In fact, let's just do the first 4 and you'll see what I mean. So, adding these together, that's 6 times 0.01, 0.06. Third term is 0.0015. And the fourth term is 0.00002. Okay, so we get a value of 1.06152. Okay, now if we only wanted accuracy to 3 decimal places or 4 significant figures, then we possibly wouldn't need, certainly wouldn't need the fourth term. We may not even need this third term. So, calculating an estimate for 1.01 to the power of 6, we can get away with the first 3 terms and produce a reasonable accurate answer. And of course this works because as x is close to 0, each subsequent term down the expansion is a lot smaller than the previous term. So when you get to the 5th term, for example, which has got the value 0.000000015, it adds practically nothing onto the total amount, and certainly doesn't affect it if we're just interested in accuracy to 3 decimal places. In example 1, we need to obtain the first 4 terms in the expansion of 1 plus 2x to the power of 8, and then work out an estimate for 1.06 to the power of 8. Then we're going to calculate the percentage error in our estimate. Now normally we could use the CAB method, and you've done that many times now, but I'm going to show you the other formula which we use when there is a 1 in one of the terms in the function. Okay, so I'm going to start off by writing down this other formula. Hopefully you can see a pattern in this. That's 2 factorial underneath that term and 3 factorial underneath that term. So there are obviously more terms here. In fact, there'd be a total of 9 terms. But the next term would be n, n minus 1, n minus 2, n minus 3 times x to the power 4 over 4 factorial, and so on. Okay, but we only need the first 4 terms, and the 1 is actually the first term. Now that's the expansion of 1 plus x to the power of n. We need the expansion for 1 plus 2x to the power of 8. So what I'm going to do is to replace x with 2x and replace n with 8. Okay, so always put brackets around whatever you're substituting in. Here we're replacing x in the first line with a 2x, so I'm putting brackets around 2x to replace x there, and then replacing n with 8. Here we've got 8 times 7, which is n minus 1, times 2x squared, and of course with brackets around the 2x we need to square the 2 as well. And remember, 2 factorial is 2 times 1. And then the fourth term, we've got 8 times 7 times 6, which is our n minus 2. 2x all cubed. That's over 3 factorial, which is 3 times 2 times 1. Okay, so that leads to 1 plus 16x plus 112. You can just type these numbers in your calculator and work them out. 112x squared plus 448x cubed. And then some other terms as well. Okay, so the next question is, how can we use this to approximate 1.06 to the power of 8? Well, we want 1.06 to the power of 8. We've got the expansion of 1 plus 2x. So if you can work out the value of x, which makes 1 plus 2x equal to 1.06, then we can use our binomial expansion with that value of x. Okay, so set 1 plus 2x equal to 1.06, and it's very simply a way of rearranging this equation. Rearrange it and work out what x is. And you can see we're going to get 0.03. So by substituting 0.03 in here, we get 1.06. We need to also substitute it into our 4 terms in our approximation. Okay. I'm going to give you a moment to do that, and we can then, I'll show you the answer in a few moments. So pause the video, work it out, and then we'll see if you've got it right. Okay, so if you've substituted 0.03 into those 4 terms, you should get the value. So I'm just going to write this down. 1.06 to the power of 8, approximately equal to 1.59286. Okay, so hopefully you got that value. Now the last part of the question was to work out the percentage error, and you need to copy down the formula for this. So percentage error is equal to the exact value minus the approximation over the exact value and because it's a percentage, we have to multiply by 100. Okay, so the percentage error, the exact value minus the approximation divided by the exact value times 100. Let's just put a box around that. Okay, so let's do that. You can, of course, check your approximation just by calculating, putting in your calculator 1.06 power of 8. You should get a value that's really close to your approximation. That's a good way of checking if you've made a mistake. So let's just go back and actually work out this percentage error. So the exact value is actually 1.593848075. I've just used all the figures on my calculator there. The approximation, which is 1.59286. So you can see they are pretty close. We've got a 1.5928, we've got 1.5938. So certainly in the right ballpark. Okay, and we're dividing by the exact value, 1.593848075 times by 100. And we get a value of 0.06%. So just by using 4 terms, we can actually produce an approximation which is accurate to 0.06%. Okay, let's have a look at the next example. In example 2, we need to find the first 4 terms of the expansion of 1 minus x over 4 to the power of 10, and then find an estimate for 0.975 to the power of 10. I'm going to give you guys a moment just to see if you can use that new formula to do the expansion. So pause the video and then we'll go through it in a moment. Okay, so let's write this down. 1 minus x over 4. Common mistake students would make is to leave off the negative, so always include the sign as well in your expansion. So you get 1 plus n, which is the power nx. So that first term is going to be negative, plus n minus 1 x squared. Another common mistake is to forget about the factorial on the bottom. So 2 factorial, I'm just going to leave it as 2. n minus 1, n minus 2, x cubed over 3 factorial, which is 6. Okay, the other common mistake would be to forget to square the 4 or cube the 4 in this particular example. So hopefully none of you have made those mistakes. So we are going to get, I'm just going to write down the simplified fractions here. 1 minus 5 over 2x. And again, you can just put these into your calculator and work them out. 45 over 16 x squared. Another little tip for you folks, even though you're dividing everything by 2 here, you can actually put it in the denominator of this top fraction. So you can do 10 times 9 divided by 2 and then divide by 16. Okay, or 2 lots of 16 in the denominator. A little tip for you. The last term is minus 15 over 8 x cubed. Okay, so that's what they would be looking for in the exam. You'd probably get 1 mark for the first 2 terms, 1 mark for getting that third term right, and 1 mark for getting it all right. Okay, so getting it fully correct. Simplified fractions and all. Now we need to do an estimate for 0.975 power of 10. So we need to equate these two. 1 minus x over 4 and 0.975, just to find the value of x that we need to substitute into our expansion. So let's just put those equal to each other. And if you rearrange that equation, you'll end up with x is 0.1. Okay, let's not go too far. Right, so now we need to substitute that value of x into our expansion. That's going to give us an approximation for 0.975 to the power of 10. So 1 minus 5 over 2 times 0.1. 45 over 16, 0.1 squared, and then minus 15 over 8 0.1 cubed, and so on. Right, so that is actually equal to 0.77625. Okay, 0.975 to the power 10 is approximately equal to that, those four terms there, but that is actually exactly equal to 0.77625. So we've gone from approximately equal to equals. Now, the exact value, if you were to put it into your calculator and work it out, you're going to get something very close to 0.77625. I'm just going to show you what the exact value is. .7763. I'll just round it to 5 decimal places so you can see. So 0.77633. We're actually only interested in our answer to 4 decimal places. So if you rounded both of these answers to 4 decimal places, you get the same value. So let's just write that down again. 0.975 power of 10 is approximately equal to 0.7763, and just put in brackets for dp decimal places. Okay, so that's it, folks. That's all you needed to do for that example. Here we're taking a binomial expansion and we're multiplying by a linear expression. So we need to work out the expansion of 1 minus 3x power 5, and we're going to multiply all of that by 2 plus x. However, we're only interested in terms up to and including x squared, because we're told in the question that x cubed terms and the higher can be ignored. So I'm going to give you a moment, pause the video, work out the expansion of 1 minus 3x to the power 5, but only the first 3 terms, and we'll go through the rest in a moment. Okay, so let's just go through it. You know, 2 plus x. Now, when you've done the expansion of 1 minus 3x power 5, you could use that second formula. I think once you get used to it, it's actually a little bit quicker than the other one, but only when there is 1 as one of the terms. That's the only stipulation they have. So you should get 1 minus 15x plus 90x squared plus some other terms that we can ignore. Now we only actually need, as a result of multiplying these two brackets together, all the terms up to and including x squared. So we could ignore, for example, x times 90x squared. That would give us an x cubed term which we can ignore. So we won't bother doing that. But we do need to multiply 2 by each of these 3 terms. And then we can take x and multiply by 1 and by minus 15x. Okay, and then just combine our like terms together. So 2 is the only constant term. We've got a minus 30x plus an x, so that leads to minus 29x. And then 180x squared minus 15x squared is plus 165x squared. Okay, so that's an example when we have a binomial expansion multiplied by a linear expression. And that's actually what we needed to show in the question, that our expansion is approximately equal to 2 minus 29x plus 165x squared. Okay, time for a little bit of practice, folks. Have a go at exercise 80. Do check your answers as you go along and tick them if you got them right, or if you got them wrong, see if you can figure out where you went wrong. And if not, we can go through it in class.